myself Bitu with the Academy of Science and Technology. Today I am going to discuss an important linear partial differential equation, which is our Lagrange's equation, and its general form is PP plus QQ equal to R. See, in this equation, you are familiar with the notations small letter p and small letter q. See, here small p is dou z by dou x, q is dou z by dou y. See, in this, capital letters p, q and r are functions of x, y and z. Next, I would like to express the method of solving this PP plus QQ equal to R. For solving this equation, there are three steps. First step is you write its auxiliary equation. Auxiliary equation of the Lagrange's equation is dx by p is equal to dy by q is equal to dz by r. See, this is its auxiliary equation. Really, these are differential equations. Step 2, you try to find two solutions of this auxiliary equation. Really, there are two methods for solving this auxiliary equation. Method 1, grouping method. Method 2, method of multipliers. You use suitable method for solving this auxiliary equation for getting two solutions. Let the two solutions be u equal to c1 and v equal to c2, where u and v are functions of x, y, z. Sometimes some variables may be absent. Anyway, in general we can say u and v are functions of x, y, z. Let us assume u equal to c1 and v equal to c2 are the two solutions of the auxiliary equation. Step 3. Now we can easily write the solution of the Lagrange's equation, and its solution is f of uv equal to 0. That is, any function of uv equal to 0 is a solution of the Lagrange's equation. And f of u equal to 0 means we can also rewrite it as u equal to function of v. See, this is the solution of the Lagrange's linear differential equation. Let me illustrate how to solve a Lagrange's linear equation. For that, you consider the equation yq minus xp is equal to z. First, you write the auxiliary equations. We know the auxiliary equations are dx by p is equal to dy by q is equal to dz by r. For writing the auxiliary equations, we need p, q and r. For that, you consider the general form of the Lagrange's equation pp plus qq equal to r, and you compare the given equation with this general equation. And by comparing these two equations, see, now given equations can be rewrite in this way. By comparing these two equations, you can see p is minus x, q is y and r is z. Next, you write the auxiliary equations. We know the auxiliary equation is dx by p is equal to dy by q is equal to dz by r. Here, dx by minus x is equal to dy by y is equal to dz by z. See, this z and z are same. That is, you can write it as z. Step 2 is you try to find two solutions of this auxiliary equation. You consider this auxiliary equation and you try to find two solutions. You can find the solutions by grouping method or method of multipliers. Here you can easily apply the grouping method. See how we can apply the grouping method. So you consider the first two derivatives, that is dx by minus x equal to dy by y. See, it is a differential equation. You can easily solve it. Almost all differential equations can be solved by separating the variables. Here, the variables are separated. That means dx is with a function of x alone, dy is with a function of y alone. Now the variables are separated. If the variables are separated, by direct integration you will get the solution of that differential equation. So its solution is integral dx by minus x is equal to integral dy by y. That is, what is the integral of left side? It is minus log x is equal to log y plus, see, after integration you have to put a constant. See, first order differential equation. Solution of the first order differential equation contains an arbitrary constant. Or after integration you put a constant. Let the constant be, see, these terms are in terms of log, so you put it as log c1. Again, by rearranging, you take log y to the left, that is minus log x minus log y is equal to log c1. That is, you take the negative sign common outside, that is minus log xy is equal to log c1. Since c1 is an arbitrary constant, you can consider it as log xy is equal to log c1. See, since c1 is an arbitrary constant, minus c1 is again same as c1. So you take it as c1. So log xy is equal to c1. That is, xy is equal to, remove logarithm on both sides, you can see xy is equal to c1. That is one solution of the auxiliary equation. See, we are trying to find two solutions of the auxiliary equation. We assume the solutions as u equal to c1 and v equal to c2. So see, this is in the form u equal to c1. We got one solution, u equal to c1 of the auxiliary equation. Next, you try to find one more solution of the auxiliary equation and let it be v equal to c2. Next, you consider this differential equation. Actually, we have to form two solutions of the auxiliary equation. Next, you consider dy by y is equal to dz by z. See, this is a differential equation and in separable form. So by integrating, you can easily write its solution. So its solution is, it is obtained by integrating. Its solution is log y is equal to log z plus constant, that is log c2. And this is log, you take log z to the left side, then log y minus log z is equal to log c2. That is log y by z is equal to log c2, which implies y by z is equal to c2. That is another solution of the auxiliary equation. See, the another solution is y by z is equal to c2. That is, now we have two solutions of the auxiliary equation. Now you can easily write the solution of the given partial differential equation. See, this is actually this is our v equal to c2. So for solving this equation, we need only two solutions of the auxiliary equation. Really, you can form more than two solutions of this auxiliary equation. For example, if you consider first and last and solving it, you get another solution of the auxiliary equation. Really, we need only two solutions of the auxiliary equation. Anyway, you try to find two solutions, that's enough. And we got two solutions of the auxiliary equation. That is xy equal to c1 and y by z equal to c2. Next, see how to write the solution of the given partial differential equation, that's our Lagrange's equation. So its solution is, we know if u equal to c1 and v equal to c2 are the two solutions of the auxiliary equation, then solution of the Lagrange's equation is f of uv equal to 0. F of uv equal to 0. So solution of this differential equation is f of xy minus f of xy comma y by z is equal to 0. This is the solution. Or you can write as, it's not necessary, xy is a function of y by z. Or you can write it as y by z is a function of xy. Okay. I hope you understand the method of solving a linear Lagrange's equation. Here, mainly we have to find the two solutions of the auxiliary equation. Really, auxiliary equation is a collection of differential equations. Here really we need the skill for solving a differential equation. Let me solve another equation. Consider y square p minus xyq is equal to x into z minus 2y. You compare this equation with our pp plus qq equal to r. So what is p? P is y square, q is minus xy, r is x into z minus 2y. Auxiliary equation is dx by p is equal to dy by q is equal to dz by r. That is dx by y square is equal to dy by minus xy is equal to dz by x into z minus 2y. Next we have to write two solutions of this auxiliary equation. For that you take suitable differential equations. By looking into the first equation, we can easily get one solution of the auxiliary equation. So, see, in this y, 1 by y is common, you can remove. So, this implies dx by y. You remove 1 by from both sides, dy by minus x, which implies, see, it is not in variable separable form. So, you rearrange, you can see minus x dx is equal to y dy. Now this is in variable separable form. By integrating you will get the solution. So solution is integral minus x dx equal to integral y dy. That is minus, this integral is x square by 2 is equal to y square by 2. After integration there is a constant c1. You take this y square by 2 to the left side. We have to make a solution in the form u equal to c1. So you take this to the left side, that is minus x square by 2 minus y square by 2 is equal to c1. You take here, there is a common factor. You take the negative sign outside. That is, see, our solution is this one. By rearranging, you take the negative sign to the right side, that is x square by 2 plus y square by 2 is equal to minus c1. Since c1 is arbitrary, you can take this minus c1 as c1. Again, you take 2 to the right side, then x square plus y square equal to 2z1. Since c1 is arbitrary, you can take this 2z1 as c1. Okay. So our solution is x square plus y square is equal to c1. So we get one solution as u equal to c1. Similarly, you try to find one more solution. For that, you consider the differential equation, this one. Really, through practice only you can decide which one is suitable for getting a solution. See, it's a skill. You try to solve many questions, then you can easily identify which equation is better for getting an easier solution. Okay. So for getting the second solution, you take this one, that is you can remove the x. By removing x, we have this equation. It's not very easy to separate the variables. See, if you know the different methods for solving a differential equation, then you can easily solve this equation. Let me solve this equation by rearranging or by cross multiplying z minus 2y dy. Take the right side to the left side. You consider these two. So here there is a mistake. It is 2y dy. You consider the first and last. Actually, it is d of yz. What is derivative of yz? What is derivative of uv? Is first into derivative of second plus second into derivative of first. That is, this can be written as derivative of uv. Similarly, by taking first and last, you can consider it as derivative of yz. Derivative of yz minus 2y dy. Now you will get the solution by integrating. Solution is integral is equal to a constant. Let it be C2. What is integral? We know what is integral of dx? It is x, because integration and differentiation are reverse process of each other. So its integral is yz minus y square is equal to y square by 2. 2 into y square by 2 will cancel and is equal to 2. That is yz minus y square equal to C2. That is the another solution of the auxiliary equation. Now we have two solutions of the auxiliary equation. So solution of the given partial differential equation is f of, so the required solution or the general solution of the given equation is f of x square plus y square comma yz minus y square is equal to 0. Or you can rewrite it as, it's not necessary, it as x square plus y square equal to a function of yz minus y square. If you get two solutions of the auxiliary equation, then you can easily write the solution of the given partial differential equation. Let me conclude this video by solving one more tricky example. Consider p minus q equal to log x plus y. So here, what is p? P is, so for that you compare with pp plus qq equal to r. P is 1, q is minus 1, r is log x plus y. So what is the auxiliary equation? It is dx by 1 is equal to dy by minus 1 is equal to dz by log x plus y. Next, you try to find two solutions of the auxiliary equation. For that, you consider first two. So, dx equal to minus dy. By integrating, we get one solution. So, integrating solution is x equal to minus y plus c1. That is, x plus y is equal to c1. So, we got one solution which is x plus y is equal to c1. Next, try to find one more solution. For that, you take another suitable combination. Let me take first and last. So, dx is equal to dz by log x plus y. See, we know x plus y equal to z1 is a solution. So, you put x plus y equal to z1. That is dx equal to dz by log c1. That is log c1 dx is equal to dz. By integrating, its solution is, so you integrate, solution is log c1 into x. That is x log c1 is equal to z plus c2. That is x log z1 minus z equal to c2. That is another solution. What is C1? C1 is x plus y. So x log x plus y minus z equal to C2. That is another solution. We have x plus y equal to C1 and x log x plus y minus z equal to Z2 are the two solutions of the auxiliary equation. Anyway, you try to find two solutions. Now we got two solutions. Then with the help of these two solutions, you can easily write the general solution of the given Lagrange's equation. So the solution is f of x plus y, x log x plus y minus z equal to 0 is the required solution. See, I already mentioned the method of solving differential equation is very important. If you know the different tricks for solving the differential equations, you can easily find two solutions of the auxiliary equation. You can achieve this technique by solving more and more problems in Lagrange's equation. Is solving auxiliary equations by the method of multiplier technique. See, we have the auxiliary equations dx by p is equal to dy by q is equal to dz by r. If L, M, N are constants or functions of x, y, z, then we have dx by p is equal to dy by q is equal to dz by r is equal to L dx plus m dy plus n dz divided by Lp plus mq plus nr. If we can choose Lmn in such a way that, say, this denominator Lp plus mq plus nr equal to 0, then you can consider its numerator as 0. That is Ldx plus mdy plus ndz equal to 0. Now you solve this differential equation, you will get one solution u equal to C1. Similarly, if you choose another set of multipliers L1, M1, N1, then you can find one more solution of the auxiliary equation. Next, let me solve this equation. This equation is in the form Pp plus Qq equal to R. Its auxiliary equations are dx by p is equal to dy by q equal to dz by r. That is dx by x into y minus z is equal to dy by y into z minus x is equal to dz by z into x minus y. Here choose L, M, N, R, 1, which implies L dx plus n dy plus n dz divided by, here L, M, N, R, 1. So dx plus dy plus dz by x into y minus z plus y into z minus x plus z into x minus y. Next, you simplify the denominator. You can see this xy cancel with this xy, then a minus xz plus this xz. Similarly, you can see all the terms in the denominator will cancel each other. So the denominator is 0, which implies dx plus dy plus dz by 0. So we can take the numerator as 0, that is dx plus dy plus dz equal to 0. It is a differential equation. You can solve it by integrating. So solution is obtained by integrating. Solution is integral dx plus integral dy plus integral dz is equal to C1, which implies x plus y plus z equal to C1. That's our one solution. Again, we have to find one more solution of the auxiliary equation. For that, you choose the multipliers as 1 by x, m dash as 1 by y, n dash as 1 by z, which implies L dash dx plus m dash dy plus n dash dz divided by 1 by x into p, that is y minus z, plus 1 by y into q, that is z minus x, plus 1 by z into r, that is x minus y, which implies, see the denominator is, this cancel with this one, y minus y, so denominator is 0. So this implies 1 by x dx plus 1 by y dy plus 1 by z dz divided by 0. So you can consider its numerator as 0. That is 1 by x dx plus 1 by y dy plus 1 by z dz equal to 0. See, it's a differential equation in variable separable form, so you can easily solve by integrating. So solution is integral 1 by x dx plus integral 1 by y dy plus integral 1 by z dz is equal to C2. That is log x plus log y plus log z. See, these terms are in terms of log. You keep the constant as log C2. Also, you can rewrite C2 as log C2 since C2 is an arbitrary constant. That is log x, y, z is equal to log C2. That is x, y, z is equal to C2. We have two solutions of the auxiliary equation. So, we can easily write the solution of the given partial differential equation. See, the solutions are x plus y plus z equal to z1 and the second solution is x, y, z is equal to C2. So, solution of this partial differential equation is function of x plus y plus z, comma, this is the general solution of the given partial differential equation. Let me answer the same question in another point of view. See, we have the auxiliary equations. See, algebraically, if we have a by b is equal to c by d equal to e by f, which implies a plus c plus e divided by b plus d plus f. So, this implies dx plus dy plus dz divided by x into y minus z plus y into z minus x plus z into x minus y. Now see the denominator. After simplifications, you can see the denominator is 0. See, if the denominator is 0, by multiplier technique, we can take the numerator as 0. That is dx plus dy plus dz equal to 0. So our solution is x plus y plus z equal to C1. See, indirectly we apply the multiplier technique. So, actually, I took this combination because if you take the sum of the denominator, you can see it's 0. That's why I had taken this combination. By looking into these auxiliary equations, if you take this as the numerator and again dy by y as the numerator and dz by z as the numerator, then you can see this is dx by x by y minus z is equal to dy by y by z minus x is equal to dz by z x minus, which implies next you take the sum of the denominator. You can see that combination is 0. So you consider that combination, that is dx by x plus dy by y plus dz by z whole divided by y minus z plus z minus x plus x minus y. See, the denominator is 0. So we will get dx by x plus dy by y plus dz by z. And solving, you can see another solution is x, y, z is equal to C2. Here also we applied the method of multiplier technique in an indirect way. Next, let me consider an example in which both methods can be applied. See the question, y square plus z square into p minus xy cube plus xz equal to 0. So its auxiliary equations are dx by p. P is the coefficient of small p. Is equal to dy by q. Q is the coefficient of small q. Is equal to dz by r. R is, see our equation is pp plus qq equal to r. You take this term to the right side and r is equal to minus xz. See, looking into these auxiliary equations, you consider the last differential equation. It is dy by minus xy is equal to dz by minus xz. You can remove this minus x, which implies dy by y is equal to dz by z. And this differential equation is in variable separable form, so you can easily solve by direct integration. And its solution is log y is equal to log z plus log z1. That is log y by z is equal to log c1. So y by z is equal to c1. That is one solution of the auxiliary equation. I find another independent solution by multiplier technique. For that, you choose the multipliers as L equal to x, m, y, n, z. Then this implies x dx, y dy, z dz by x into y square plus z square minus xy square minus x z square, right? Implies x dx plus y dy plus z dz by, see, xy square will cancel with this one and the xz square cancel with the minus xz square. So you can see the denominator is 0. So you can consider x dx plus y dy plus z dz equal to 0. See, this differential equation is in variable separable form. So by direct integration you can easily write the solution. So solution is integral x dx plus integral y dy plus integral z dz is equal to c2. That is x square by 2 plus y square by 2 plus z square by 2 is equal to c2. You take 2 LCM and you take 2 to the right side. Then right side becomes 2z1. Since c1 is arbitrary, you can consider it as c1. So the second solution is x square plus y square plus z square equal to c1. Now we have two solutions. So solution of the given equation is f of y by z, x square plus y square plus z square equal to 0.